Thanks for having me at this seminar. I'm really excited to be here. And as said before, today I'll talk about improving robustness distribution shifts. So standard machine learning models are trained under the assumption that training and test data are drawn from the same distribution. Under this IID assumption, as we all know, machine learning models have achieved high performance on a wide range of tasks. However, this assumption doesn't often hold up in the wild. The data distribution often changes from training to test time, resulting in what we call distribution shifts. These distribution shifts can significantly degrade model performance in many real-world applications. So, for example, models are often trained on a few data sources, but with the goal of deploying it in many other settings. In autonomous driving, models might be trained on data collected in certain locations, but they need to maintain high performance even when they're deployed to new locations. In another example, models can perform well on average, but systematically fail on groups of data that are underrepresented in the training set. State-of-the-art speech recognition systems work well for most users, but they can perform poorly on Black speakers. Finally, models can latch onto spurious correlations and fail on examples where these heuristics don't hold up. When models are trained to diagnose pneumothorax, they can learn to associate the disease with its common treatment, concretely a chest drain shown here. And consequently, these models can perform poorly on test X-rays with untreated pneumothorax, where there are pneumothorax but no chest drain. All of these examples motivate the overarching goal of this talk, which is to improve robustness of distribution shifts. And concretely, we want to maintain high performance even when there are distribution shifts. This talk will have two parts. First, we'll consider a more idealized scenario concerning spurious correlations, and we'll talk about a method for mitigating this issue. In particular, we'll work with a classical technique called distributionally robust optimization, and we'll bring it to the modern regime of deep neural networks. In the second part, we'll broaden our view to other distribution shifts in the real world beyond just spurious correlations. And we'll talk about a benchmark for these real-world shifts called bios. So now let's jump into the first part of the talk. This is showing work with Plummet, Tatsu, and Percy. So as we've alluded to earlier, models can latch onto spurious correlations, which are misleading heuristics that work for most training examples, but do not always hold up. To make this concrete, consider a task to classify between water birds and land birds. Even if the model has good average error, it can be classifying the background instead of the actual object, relying on the fact that most training examples show water birds on water backgrounds. But this association does not always hold up. Water birds might be pictured on land, and the model would perform poorly on such examples. As another example, when models are trained to predict whether a person has blonde or dark hair, they can pick up on spurious correlations with demographics such as gender. And these examples share a common structure. There is a spurious attribute that is strongly but not perfectly correlated with the label. To make this concrete, in the water birds example, the label is the bird type and the spurious attribute is the background type. And this splits the data into 4 groups. In the majority groups of the training data, the spurious correlation holds up. But in the minority groups of the training data, the relationship is flipped. Now, when we train models by minimizing the average loss, the models perform well on average, 3% error in this case. However, these models can pick up on the spurious correlation and fail in minority groups. As a result, the model has high worst group error, in this case 40%. And in terms of the setup, we assume that we know these 4 groups a priori. In addition, each training example is annotated with these groups and is composed of X, Y, and the group G. At test time, we assume that we don't have any group information. So what does this mean exactly? This means that we still train a model that takes in X and outputs Y as usual, but the training algorithm can leverage group information. Our broad goal is to be more robust to these spurious correlations, and we concretely aim to achieve low worst group error. So the question is, how can we train such models? Instead of minimizing the average loss, which we refer to as empirical risk minimization or ERM, we directly minimize the worst group loss. We call this approach group distributionally robust optimization, or group DRO. So if you look at the group DRO objective, it simply computes the average loss for each group G prime, and then it takes the max over all of the groups. And now this minimax objective might look difficult to optimize, but we propose a simple stochastic optimizer and provide convergence guarantees. In each iteration, our optimizer first estimates group weights that measure which groups are the worst case, then computes the loss weighted by the group weights, and finally does a gradient update on the model parameter. And in addition to theoretical convergence guarantees, we also empirically observe that group DRO converges in a similar number of iterations as the ERM. So now that we're ready to apply group DRO, how does it work in practice? We first walk through the results on the phase dataset introduced earlier, where we train a standard ResNet 50 model. Let's look at the standard approach, or ERM. A standard approach of ERM, or minimizing the average loss. As we've discussed, this leads to low average test error, but high worst group test error. However, the training error is 0, both on the average and for the worst case group. Comparing the test errors with the training errors, we see that the worst group test error is high because the model generalizes poorly on the worst case group. This has implications for applying group DRO. Group DRO controls the worst group error only at training time and does not solve the generalization issue. In fact, from the perspective of training error, the ERM model is already robust, achieving 0 worst group training error. So with this in mind, ERM and group DRO are expected to yield roughly the same models. And in fact, that's what we observe. When we naively apply group DRO, it does not resolve our worst case error problem on neural networks. The worst group error is still high due to poor generalization. These are new challenges with respect to prior work on worst case performance and DRO. Prior works have largely focused on settings in which train and test error were similar for the worst case group because they work with small convex models or generative models. In these cases, naively applying group DRO was effective. In contrast, we work with state-of-the-art neural networks, which suffers high worst group test error despite 0 training error. In this regime, naively applying DRO yields no improvement, as we saw in the previous slide. So now, how can we solve the problem that we have 0 training error, but high worst group test error? How can we effectively apply group DRO to neural networks? A classical solution is to regularize, for example, via L2 penalty or early stopping. This is a bit counterintuitive with respect to recent trends to train more complex, more over-parameterized models to improve average error. Yet, we observed that when coupled with regularization, group DRO improves worst group error successfully. When we use a strong L2 penalty, orders of magnitude stronger than the standard L2 penalty used for these models, training error is no longer 0, and the worst group training error is much higher than the average error for ERM. In addition, even for the worst case group, the generalization gaps are small. Now, minimizing the worst group loss via group DRO leads to low worst group test error. In this paper, we similarly show more tasks that group DRO with appropriate regularization improves worst group error, in particular for the waterbirds example and for that multi-NLI dataset, which is an NLP dataset. We also observe similar trends with other ways of regularizing models, such as early stopping, in addition to L2 regularization. In summary, we have proposed group DRO as a method for mitigating spurious correlations, and more generally, distribution shifts across groups. To apply group DRO to neural networks, we saw that it is crucial to regularize a model strongly. much stronger than we need to in order to achieve good average performance. And zooming out of it, this is true not just for DRO, but any technique that relies on weighting the data in special ways. This importance of complexity control is also interesting in the light of recent works on overparameterization. Recent works have shown that overparameterization, or directly increasing model size, improves average error even beyond the point of zero training error. However, when it comes to worst group error, our results thus far hints that the opposite is true, at least in terms of model capacity. The more we constrain the model through regularization, the better worst group error is. In fact, in a follow-up work with Aditi, Panway, and Percy, we show that overparameterization indeed hurts worst group error. We also understand why this is the case both through theoretical analysis and controlled simulations. In another follow-up work with Eric, Panway, Anani, and Percy, we've also studied spurious correlations in the context of selective classification. With selective classification, models can choose to make predictions as usual or abstain. Now we might expect that this may help improve worst group performance since models could now abstain on out-of-distribution examples. However, when models are trained via ERM, selective classification can actually degrade worst group performance. In the paper, we characterize this phenomenon both empirically and theoretically, and we observe a nice connection with the group DRO work. So in order for selective classification to improve worst group performance, the worst group performance has to be reasonably good without any abstention, and group DRO is a reasonable way to train such models. In fact, for group DRO models, we see that selective classification improves worst group error further. And that's it for the spurious correlation and method part of the talk. And now I want to switch gears for part 2, which is about the Wallace benchmark for real-world distribution shifts. I've co-led this project with my lovely Panway, and this was joint work with many great collaborators pictured here. And for this part of the talk, I want to broaden our attention back to distribution shifts in general, beyond just spurious correlations. As we saw in the beginning of the talk, distribution shifts are ubiquitous in many real-world applications. In fact, as we started working on this project, we talked to many domain experts who are applying machine learning to various applications, and this uncovered many examples of distribution shift that they were grappling with. For example, in wildlife conservation, distribution shift across cameras is a challenge. To monitor wildlife, conservationists deploy static cameras in wildlife habitats, and they use machine learning to classify animals and images from these cameras. These machine learning models are typically trained on images from existing cameras and then deployed to new cameras that are unseen during training. However, different cameras vary widely in background, illumination, camera angles, and animal frequencies, and as a result, model performance can drop substantially on new camera deployments. This distribution shift is an example of a domain shift, which is where each camera is a domain, and the goal is to generalize to new domains at test time. As another example, distribution shift across regions can be a challenge in satellite imagery. Here, the task is land use classification, and different amounts of data may be available from different regions around the world. For example, we might have more training data from the Americas than from Africa, and this could cause the model to do much better on the Americas than on Africa. As a result, the model has poor worst group performance, where the group in this case is the region. This is an example of a subpopulation shift, where the test distribution is a subpopulation of the training distribution. Concurrently, domains, which are regions in this case, now overlap between training and test time, and what changes instead is their relative proportions. There are many more examples of distribution shifts across a wide range of applications. In medicine, models are often trained on a few hospitals, but must generalize to other hospitals. Similarly, in computational biology, models must generalize to data collected in new experimental patches. In agriculture, models for automatic crop analysis, such as detection models for wheat heads, Let's generalize the images from new regions, growing conditions, and crop types. And in toxic comment detection, models need to be accurate regardless of demographics. So distribution shifts are a serious problem in many applications. And one big obstacle to our progress on these shifts is that real-world distribution shifts are understudied in machine learning research. My work on distribution shifts has focused on very different kinds of shifts from what we just looked at. Instead, it's common to focus on synthetic shifts, for example, by changing their colors or adding noise. And in our own prior work, we simply cut and paste birds onto different backgrounds. Other datasets split data in ways that induce fairly extreme shifts. For example, in the domain net dataset, models are trained on photos but then tested on sketches. These existing datasets are important, challenging test beds, and a lot of work has gone into developing methods to handle them. For example, the fixed match algorithm uses unlabeled data to adapt to the test distribution, and it substantially improves auto-distribution performance on domain net. The question we were interested in, however, was how well does success on these standard benchmarks transfer to other shifts in the wild, like shifts across hospitals or farms or wildlife cameras? That is, by hill climbing on these standard benchmarks, are we actually improving our robustness of these shifts in the wild? To answer this question, and more generally, to help researchers study a broader set of distribution shifts, we introduce WILDS. WILDS is a suite of 10 datasets capturing the kinds of distribution shifts that ML models face in the wild, across diverse application areas and modalities. The benchmark includes the earlier examples of distribution shifts that domain experts were grappling with. These domain experts have collected data on each of these tasks, and in WILDS, we built on their efforts by curating, adapting, and standardizing these datasets and bringing them to the machine learning community. Each of the WILDS dataset considers shifts across domains, where domains are cameras, hospitals, experimental batches, demographic groups, and so on. The datasets fall into the settings we discussed: domain shift, subpopulation shift, or a combination of the two. For each dataset, we consider a setting that reflects the real-world challenges in the application. To quickly walk through the benchmark, here are the datasets that have exactly the setting that we discussed in the earlier examples. There is iWellCam, Chameleon, RxRx1, Global WeHead Detection, Civil Comments, and FMOW. One exception is that in FMOW, in addition to the subpopulation shift over regions, we also consider a domain shift over time. And in addition to these datasets, we have OGV multi-CPA, where we consider a molecule property prediction task, and we seek to generalize ANSI scaffold structures. And in property map, the goal is to predict asset wealth across many countries and regions. And in Amazon, we consider sentiment classification task across a diverse set of users. And finally, in the Pi150 dataset, we consider the code autocomplete task where the shift is across different GitHub repos and token types. To design WILDS, we identified and adapted datasets that fit the following criteria. First, as we've discussed, the dataset should reflect a distribution shift that's likely to arise in a real-world setting. Secondly, we selected datasets on which the distribution shift caused a large drop in model performance. And lastly, each dataset should have enough sources of leverage to train a robust model. I will now discuss the latter two criteria more, and I'll first elaborate on the performance drops. To measure performance drops due to distribution shifts, we train standard models via empirical risk minimization, and then compare their out-of-distribution performance and in-distribution performance. Out-of-distribution performance is model performance with distribution shifts, and we measure this using the default WILD splits. In-distribution performance is a model performance without distribution shifts, and we measure this by evaluating on a held-out set without any distribution shifts. The larger the difference between in-distribution and out-of-distribution performance, the larger the effect of distribution shift on model performance. And here are the results on the WELS dataset. As you can see, the out-of-distribution performance is much worse than the in-distribution performance, and the gaps are large for all datasets and wilds. In other words, these distribution shifts cause large drops in model performance. And returning to our criteria for WELS datasets, our last criterion is the potential leverage. We wanted our datasets to be non-trivial but also tractable because models cannot be expected to extrapolate to arbitrary distribution shifts. To this end, we provided auxiliary information that would provide some structure to the distribution shift. For example, in each of the WELS datasets, the training set is made up of multiple domains, and this provides some information about how the data shifts across domains. In addition, we provide domain annotations and other metadata at training time so that training algorithms could leverage the domain structure in order to train robust models. And furthermore, recently we released the version 2 update to WELS where we added unlabeled data as additional source of leverage. And I'll elaborate on this next. First, why is unlabeled data a promising source of leverage? Unlabeled data is often available in large quantities, including from distributions beyond the training distribution. In WELS, we provide unlabeled data from various types of domains. First, we have unlabeled data from source domains, which make up the training distribution. This type of unlabeled data can be used to boost in-distribution performance, which could translate to better out-of-distribution performance. Secondly, we have unlabeled data from target domains, which make up the test distribution. This type of unlabeled data would allow us to adapt to the test distribution via domain adaptation, and this has been successful in standard benchmarks that we saw earlier. Finally, we have unlabeled data from extra domains, which are neither in training nor test distribution. This type of unlabeled data may tell us what kind of variation we might expect to see across domains, or help us learn representations that work well across domains. For example, in the global weehead detection dataset, we provide unlabeled data from all types of domains. The task here is to predict the bounding boxes around weeheads, and the distribution shift is mainly across locations. We have unlabeled data from source domains such as Belgium and France, from target domains such as the United States, as well as from extra domains such as Canada and Japan. Unlabeled data was readily available from all types of domains since the images are collected in hundreds of institutions around the world, but only a small subset of them gets labeled due to the high labeling cost. Overall, we provide unlabeled data for 8 out of 10 datasets in WELS. There are 14.5 million labeled examples, and this expanded the number of samples for each dataset by 3 to 13-fold. This version 2 update, which adds unlabeled data, keeps all labeled data and evaluation metrics unchanged, so any results on this updated version can be directly compared to results on the original benchmark. Now that we have WELS, we're equipped to answer the question from the beginning of this section: the success transfer across different distribution shifts. As we saw earlier, methods from prior work improve out-of-distribution performance on standard benchmarks like DomainNet. So now, how do these algorithms perform on WELS? We benchmark representative methods from the domain adaptation literature, and we consider 3 classes of methods. Domain invariance methods, which learn representations that are invariant across domains. Self-training, which train on unlabeled examples that are pseudo-labeled by a model. And self-supervision, which learn representations from unlabeled data by training on auxiliary proxy tasks. We benchmark a total of 7 methods listed here. Concurrently, for each WELS dataset, we run these baselines on unlabeled data from target domains whenever this type of unlabeled data is available. And for the 2 datasets without any type of unlabeled data, we use unlabeled data from extra domains instead. Then we compare these methods to standard training without access to any unlabeled data, which we call empirical risk minimization, or ERM. Before we look at all methods, let's first focus on fixed match, which is the best performing algorithm on the mainnet. As we saw earlier, fixed match does really well on the mainnet. Compared to ERM, fixed match improves outer distribution performance substantially from 36% to 50%. However, on image classification datasets in wild, we find that fixed match could be even worse than standard ERM, which doesn't even use any unlabeled data. We observed similar trends on other methods and other wild datasets, and no methods consistently outperformed ERM. In this table, we report the performance of applicable algorithms on each of the wild datasets. We highlight the results in green if the method outperforms ERM on the dataset, and we highlight the results in red if the method fails to do so. As you can see, although the results aren't as extreme as it was for fixed match, methods still often fail to outperform ERM. In fact, we only see methods significantly improve over ERM in a few cases, namely for noisy student and SWAB on Chameleon and FMOW datasets. Overall, these results show that successes on standard benchmark often doesn't transfer to other shifts in the wild. Furthermore, we see no improvements in modalities and tasks beyond image classification, which haven't been studied as much in prior work. So why might current methods struggle with these modalities and tasks? One factor at play could be data augmentation. Data augmentation plays a key role in the two methods that did improve out-of-distribution performance, which are noisy student and SWAB. However, augmentation techniques are much more well-developed on images than on other modalities like text and graphs, which could have limited the method's success on these other modalities. Separately, some methods haven't been studied as much on some tasks, such as self-training algorithms for regression tasks. And finally, methods weren't successful when unlabeled data came from extra domains instead of target domains. For example, unlike other image classification datasets, we saw no improvements on the IWALChem datasets, which has unlabeled data from extra domains only. This is somewhat expected since some of the methods were designed for unlabeled data from target domains, but it also calls for future methods that can leverage extra domains more effectively. Overall, we saw that success often doesn't transfer to real-world distribution shifts. These results tell us that in order to make progress on real-world shifts, it's not enough to work on just the existing benchmarks. We also need to develop and evaluate methods directly on these real-world shifts that we care about. So we encourage everyone to try out the wild datasets. We have a leaderboard on our website where we are accepting submissions. We'd also like to encourage the broader ML community beyond just distribution shift researchers to test their algorithms and models on wilds, because dealing with these distribution shifts is an important part of deploying ML models in many real-world applications. Wilds is easy to use and available as an open source library. With just a few lines of code, you can download a dataset and prepare data loaders, train a model, then evaluate it with a standardized function. In addition, we provide default models for all datasets, so all you need to do is to plug in your algorithms. I'll end by discussing how we can build on and go beyond wilds. We've covered distribution shifts in 10 different ML applications, but these are really just a small sample of what's out there. In many important application areas, it was difficult to find a suitable dataset. For example, as mentioned earlier, prior work has shown that commercial speech recognition systems do poorly on some demographics, which made this a natural candidate for a subpopulation shift problem. However, among existing publicly available datasets, we did not manage to find a training dataset with enough demographic diversity. As another example, in medicine, one of the challenges concerned the tractability of distribution shifts. For example, across time and hospitals, there may be changes in the relationship between the input and the label, and this might make it impossible for a model to generalize unless they're given some additional information. For other application, we found some candidate datasets but did not observe substantial drops due to distribution shifts. For example, in the BDD 100K autonomous driving dataset, we found that if the training set includes both day and night images, then the object recognition performance is not that different between daytime and nighttime. And when we studied demographic fairness in the stop and frisk policing dataset, we observed substantial performance disparities across demographics, but found that these were due to biases in the data instead of the distribution shift. In our paper, we discussed several of these application areas in more detail and the challenges of finding suitable datasets in them, including case studies of BDD and SQF datasets shown here, a genomic dataset, and a couple of review datasets. Overall, the datasets in WELS are really just a start, and there is still a lot more that we as a community can do on the datasets front. Already, there are many interesting open research questions involving real-world distribution shifts. For example, how can we characterize all of these distribution shifts and their effects? What kinds of algorithm will allow us to be robust to these shifts, and what leverage will they use? We hope WELS will be a useful tool that encourages future work on real-world distribution shifts. And with that, I'll conclude by saying a big thank you to all of the researchers that helped us along the way. Thanks for listening, and happy to take any questions.